All right. Today I want to talk about a completely different model, and this is modeling the Xerox machine. The reason I call it a photocopy machine is because the problem came to us not from Xerox but from Kodak. They are competitors. They live in the same town in Rochester, New York, and in the Kodak country you don't say Xerox machine. Also, our friends at 3M will not be happy to if I talk to them about the Xerox machine. So it's a photocopy machine. Now, I'll tell you what happens when you push the button and you get a nice copy after, sort of nice copy afterwards. So this is has a very interesting mathematical parts to it, and basically we speak of the Xerox machine. It's at least at Xerox. And they have what they call several engines, or you may call them stations, or dividing it to sub-problems. So the first one is the charge. So what happens here is that in the machine there is a set of wires, and a high voltage is given to the wires, and when wires are in high voltage in air, they create ions from the air particles, positive ions that are around. This is called a space charge. And that's an interesting problem in itself, the equations of the space charge, which involve the density of the charge and the electric field coupling together. But I'm not going to talk about this today. So this is here the corona, and this this is a wire here that is given up to 5,000 degrees voltage, very high voltage, and that charges, that creates positive ions, and they migrate to the surface. This is a photoconductor drum, or a photoreceptor. It's about the size of a fist. And there are various models. The one that I'm talking here, the photoconductor makes one revolution for every page that you Xerox. So these particles, the positive particles, are migrating here, positive ions, and they stick to the surface here, or penetrate it, and they lie on this surface. That's the first step. So this is the charge, the corona charge, and it prepares the machine for the next step. The next step, you push the button. You see a red light, a green light. What happens here is your document, and light goes through the document and pass several mirrors. Actually, in many versions, these two mirrors are moving and scanning the whole page. So it's not done instantly, but they are scanning it back and forth. And what happens through the white part of the document, the light can go through. To the black parts, which is printed part, they cannot go through. So what you get in the back, if you looked at it, you will see dark and white spots. And what actually happens here is that the places that were white on the document, the light goes through and hits this photoreceptor drum. Okay? So this is a part which okay, so so you obtain here a charge. Well, what you get here is a distribution of light particles. These are photons. Distribution of photons that are coming on into this zone. And here is what they do. I decided this morning that I'll go through this explanation here. So here is what they do. So the photoreceptor base was here. Here are the positive particles that came from the corona charge. And we assume that they are distributed nicely. There is also, at the same time I didn't talk about it, there's also charge of a corresponding charge on the other side, which is electrostatic charge of negative particles. Now, whether they are positive, there has to be negative if there was nothing before. So there is a negative charge here of electrons, and there is a positive charge. This is before you push the button. Now, as you push the button, light came and hit this layer. This is a layer where the positive particles penetrated. This layer is called the generating layer. Here. So this is, I'm sorry, the particles, the positive ions are here. In here there is another layer. It's a polymeric material, which is a generating layer. This is a layer such that when photons hit it, they easily break the atoms into electrons and into, well, they displace, they get rid of some of the electrons. They pull them out from the atoms. When you pull an atom, an electron out of the atom, then there remains a little hole in the electron. And I'll be very crude and say these are holes. So you have electrons and you have holes. So electrons, you know, form a charge, but holes also behave like a charge, and like a positive charge, because there is no reasons for that. Okay. So here the light is falling on a spot here that was white part of the document. It hits atoms in the generating layer, breaks them into electrons and into holes, and the negative ones are attracted to the positive field that was created in the corona charge. So they are just grounded. So the electrons that are generated here from the light, from the photons, just get grounded and become neutral. Don't play any role. But the holes that developed here, they start moving around. And where are they going to move around? Well, there are here electrons. They can help them out. That are attracting them, so they are moving up. So what happens is that if there was a light part of the document here, then there are a bunch of positive of holes that are going to move up into this layer here. This is a transport layer. And they are coming up, they are migrating up to where the electrostatic charge was. Okay? This migration, again, can be modeled mathematically as a diffusion process in an electric field. And again, I'm not going to talk about this. Now, as they are coming up here, they are becoming neutralized by the electrons, and the result is that we get here and negative charges that are negative or zero will be zero here, still negative here, zero. Wherever there was white in the document, correspondingly here, there will be a zero charge. So here is a profile of the charge density in this little photoconductor surface. This corresponds to a white part of the document. This corresponds to a black part of the document. White part and black part. We can also reverse it by just taking a field, something that changes it. You can reverse, there are simple mechanisms to reverse. So, but anyway, the profile of the page that you have seen, if it were a linear page, just one line, will be like this. That's not quite precise because you don't get that neat step function. It will be a little bit blurred. That's why the Xerox copy is never 100% clean. Okay, so this is the electric image of the document that you want to Xerox. Now we go back here, and we are at this point. At this point, we are here. So we exposed the document to the charge on the photoconductor, and we created here an electric image. Electric image is not something that you can see. You cannot see charges. So what we want to do is to convert the electric image to a visible image. And this is done in this step, the development stage. So here there is a magnetic brush, the developing system, and I'm going to talk about this in a little while. But let's go on with the next step. The next step is that after you got on the surface of the photoconductor, you got the visible image. It's still very messy. It's just lying on a piece of glass. You want really to get it on paper. So you transfer a paper, there's a paper path. There should be rollers here and here. The way this moves very much reminds me of the magnetic tape between two guides. And that quite often happens in problems with industry, that they are so unrelated problems but the same mathematics. And it goes over here. Here there is a fuser, which is a hot stuff that makes sure that the wet, is not quite wet, what is going to come here is a toner, which is a dry ink, but you still have to glue it to the paper. That requires heat. So the fuser sort of pushes and so the wet stuff here, the sort of dry, a little bit wet maybe, stuff here goes onto the paper, goes between through a fuser, and then it sticks permanently. The paper, it sticks permanently to the paper. You get a warm paper, as you know. In very good Xerox machines, the only way to tell that which is original is by seeing which one is warm. And you get the stuff here, the paper here, but the machine goes through one more step. You have to clean everything. You have to clean the toner that was here because not all of it was used. You have to clean, you have to get rid of the charge that you put here initially, the positive and negative. So you have to have a transfer corona, takes back all the charges. And what else? Clean lamp. Okay, these are all the cleaning stuff. And then it's ready for the next step. I think it will immediately create a charge and wait for you to push again. So these are the 7, let's see, 6 or 7. There is a charge, the expose, development, transfer, fuse, and clean. 6 engines, or 6 stations for the Xerox machine. Each one has very interesting problems. Except for this, I don't actually know people that have modeled it, but all the others are all kinds of models. And now I want to concentrate on what happens that as an electric image becomes a visible image. So the first thing to do is to magnify the picture. And here it is, except it's upside down. This is a system of magnets, and here are these little circles here are little balls. They carry the toner. So the toner is some kind of a black powder. You take these little balls that are size of 1/10 of a millimeter, and you dump them in this powder, and then you mount them on the toner carrier. And how do you mount spherical particles onto a sphere that they'll stand there, that will not roll away? By magnetic force. or by some kind of a charge. So these particles are charged, and then you push them through a channel, and this pushing done again by some kind of electric force that pulls them in. And then they are magnetized by the system here of magnets. And you know, when particles have magnetic power, they like to connect to each other, create chains. And so you get these chains or whiskers that come in here. And all of them are sort of dirty. They all carry the toner in them. Each of these circles is this here. Okay, now the photoconductor comes near this magnetic brush roll. It comes nearby, not quite touching it. In order to touch it, you'll have to have, these whiskers will have to have a special reason to be attracted here. Now remember, they carry a charge, a negative, say a positive charge. They will be attracted to the area here which has a reverse charge. They will not be attracted to the area which has the same charge. So they will be attracted, positive particles will be attracted to the negative part. And when they are attracted to it and rub against it, they put a little dark spot there. So you'll get dark spot where there was a negative charge. Or maybe it's the other way around, the positive charge. But dark spots will cover areas, let's say, that originally in the document corresponded to dark spots in the document. So dark spots will create some kind of well, the document will translate into a step function, on each line a step function, and of charge densities, and these whiskers will be attracted to the top of the stair, not to areas that correspond to the bottom of the stair, and they are attracted there, they touch the photoconductor and deposit some of the powder on these spots. And that's how you will get the document written on the surface of the photoconductor, will be written by dark spots, black spots, and white spots. Actually, it's amazing that the Xerox machine works. It's a miracle, because this is, but not for other reasons. But if you think about, you know, the distribution of this, the field is not quite, doesn't quite go. These particles of the holes, the positive charge doesn't quite go vertically. It diffuses everywhere. And then these whiskers, you know, there is a lot of randomness there. And it may rub or may not rub exactly there, but somehow it works. Of course, if you try to use a copy to make your second copy, and then use the third copy from the second, it will deteriorate quickly, and you will find that after maybe 10 copy after copy, the nth copy is coming from the n-1 copy, you'll find that if n is 10 or something, you already can see it very clearly. Although there are some actually positive results of this. You know, we had to have once, we wrote a report on mathematics in manufacturing, and we needed, Siam published it, and we needed a cover, and we took a cover of, from GM, they have an assembly line with robots. So you want to take the picture of the robot in the front to show how mathematical, you know, robotics is a mathematical area, is important in manufacturing for automobiles. But the picture of the robot was horrible aesthetically, and you couldn't really recognize it. And we kept faxing to each other, should we cut this part from the robot or that part, and eventually we got a beautiful picture because the fax machine, it was faxed actually, not Xeroxed. But so the fax machine made such a distortion that it came beautiful. And that if you ever look at this report, you see the front page, the picture, it looks very nice, but it's not the real one. It's a false fax copy of it. Now, anyway, so now let's go now to the visible region and see what happens there. So this is where I just changed everything by upside down. So this is where the negative part corresponds to a black, say negative charge corresponds to a black spot in the electric image. And here is how the toner particles start to accumulate around it. This substrate is moving, and eventually it's going to get out of the development. So there is only a certain amount of time for the toner particles to build in and form a certain thickness. The thicker the thickness is, the more black it will look. So here it starts to accumulate layer by layer, or continuously actually. I just drew here say a particular time, and then the next, after a little while longer, it will get thicker and another layer will come. There is electric field in this whole zone, but there is no charge here, there is no charge here, there is only positive charge here, and here there is this thin layer. So if phi is the electric potential, it satisfies the equation Laplacian phi is minus the density of the positive charges with some constant, which is 4 pi divided by what's called the permittivity of the space. And this boundary keeps going according to a formula which says that the surface velocity is equal to the normal vector scalar dot product with the gradient with the electric field. Electric field keep pushing or pulling it and filling in this this image. So now here is a mathematical problem. I take u equal to minus phi. So this is a Laplacian. There is no charge here. So Laplacian u is 0 here, it's 0 here. This is what the toner region is. So Laplacian u is equal to positive constant. I take it to be 1. So Laplacian u is 1 here, 0 here. And now there is a high voltage here. So u is equal to a large constant. Here u is equal to a smaller constant. We can take it 0. And we just take a part of one little letter, or one little box. And so this is a black part of the document. This is a white part of the document. And we just box it and look at it as one unit. We just want to see what happens there. I mean, the purpose of modeling here is in order to be able to choose the best parameters to get the best image. So why take a complicated thing with the whole page? You just take one letter and see how to improve it there. That'll give you a good guess. So we just take one symbol. There it is. So one white spot, one black spot on a document. Take a whole page, take one little, say, hyphen, Xerox it, and assume it's one linear, and that's what we get here. So this will be the dark part, and so Laplacian u is 1 here, Laplacian u is 0 here. This is a Neumann condition. The x derivative is 0 here and there. This is where the charge was. A charge on a thin layer is, okay, so here means that there is a jump in the electric field. Boundary layer of a charge means a jump in the electric field or a jump in the y derivative. So the function u along this line has a jump. The y derivative, if you come from above, minus the derivative if you come from below, the difference is a constant minus sigma on this interval. The ideal thing would be if this is the interval minus gamma gamma, that the visual image, the visible image, will be like this, will be a square. That will be perfect. Then you'll get 100% precision of conversion from the electronic or electric to the visible. If the electric image was 100% right, and if the image here would be exactly a square, then you will have the perfect machine and you'll make lots of money. Of course, if you have to have a good salesman organization and advertisement and so on. But this will never happen. It cannot happen. I didn't finish stating what the problem was, you see. That boundary here, over there, is not just any boundary, because remember how it goes. It has to go such that the velocity of this boundary as it keeps going is proportional to the electric field there, which is a normal derivative of u. Now, when you want to solve an equation for Laplace u equal to something, to 0 or to 1 here and some jump in, what you have to know is boundary conditions, and then you can solve it. So you have boundary conditions here, 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 and here. Then you should be able to solve it. But we don't really know where the equation satisfies Laplacian u is 0 when its Laplacian u is 1, because we don't know this boundary. This boundary is not known. In fact, it's changing. It's moving in time. So we need another condition to tell us where the boundary is, and the extra condition is this, that the velocity varies, the velocity of the boundary varies according to the derivative, normal derivative of u. So this is an extra condition to determine the boundary in a domain, a part of the boundary, well, to separate the two equations satisfied. And this is what's called free boundary problem. A problem where you have to solve an equation, but part of the boundary is not known, and you are given an extra condition. And such problems are very tricky, because sometimes you can solve it, sometimes you cannot solve it, some maybe many solutions, and so that's where this equation belongs. And it's there is a whole theory on free boundaries, but this is not included. It's not unusual that you take a problem that in real life and it's not included in the general theory. Some of them are, but not all. So how are we going to solve it? So here is an approach that we may think of. See, let's suppose that the boundary is known. Okay? Let's suppose that this boundary is known. The boundary of the toner. Of course it's not, but suppose it is known. Suppose we knew it for every time t. Okay, so we'll be able to solve for u in this domain for any time d. So suppose that we know this boundary, gamma of t, for any time t, and we solve the equation. I mean, I wrote here, I just try to impress you by writing this complicated thing. This means that the Laplacian u is 0, is 1 in d of t. It is 0 outside, because that's a characteristic function of the domain. And this means, this is sigma, by the way, and this is 2 sigma. This is 0 outside this line, which was the surface of the photoconductor there. But on the surface, Laplacian becomes, it's a unit measure. And then this becomes, okay, when the Laplacian is a Dirac measure, if you use the generalized function and so on, this means that the y derivative has a jump. It's the same thing in writing the equations in a sort of a distribution sense. It has a jump, and the size of the jump is 2 sigma when x is between minus gamma and gamma, and 0 when you are outside, because then the characteristic function is 0. So that's the same equation system that I wrote before. So for any family of curves, you solve this. Now you know the domain. If you know the curves, you solve this. And after you have solved the equation, then you compute the derivative of the equation on these curves gamma of t, and you get velocities, and you use the velocities, which is a derivative, to compute a new family of curves. And if you are lucky enough, so you compute a new family. And if you are lucky enough, and this new family will be the same as the old family, then you solve the problem. So we have here a strange kind of mapping. We start with the family gamma of t, of curves. So initially there was nothing. There was no, everything was white. The toner started to build from nothing. Then, so we take a family that starts with straight line, building up, building up, building up. For each of them, we solve this equation. We compute the velocity, the normal velocity, the derivative of u on each of these boundaries, gamma of t. And using these velocities, we integrate curves. If you know how they change in time, you can integrate back, and you get a new family of curves. And there is a mapping from one family to another family. And the question is, does this have a fixed point? That's a fixed point theorem for a family of curves. One of the problems here, the initial problems, is that just giving a curve without parameterization is very vague, and you cannot really show any fixed point if the thing does not have a unique kind of unique entity. To do analysis, you have to have something specific, not just a curve. You have to have a parameterization of a curve. So what I just said, let me write it again, formulate it again here. So now with parameterization. So here is a family of curves. Lambda is a parameter. Lambda varies between, say, minus lambda 0 and plus lambda 0. Okay? And I don't know what lambda 0 is. But we will assume this kind of parameterization. And for every time t, there is such a curve. And for every time t, say, from 0 to some time capital T. Okay? Initially, the curve is flat. You see, y of 0 and lambda is lambda, but the y, x of 0 lambda is lambda, but the y is 0. That is horizontal. So horizontally, simply x is equal to lambda. Trivial representation of the curve. And at the points plus or minus lambda, y becomes flat because it went down to the level, horizontal level. This is the velocity of the curve, dx dt, dy dt, the partial derivative in time. And if we take the dot with the normal, we want this to be the normal derivative of u. Okay? What does it imply for dx dt and dy dt? Now, it's a little bit strange because this is one scalar equation, right? Just one equation. And if you write what it means, you get two equations. So how come? One equation becomes two equations. Well, you see, I'm not asking you the right question. If you translate this to see what it means for the x dt dy dt, you find that it's equal to this plus a vector which is tangential to the normal, which is perpendicular to the normal. So a is any function times, and the x d lambda, dy d lambda is a tangent. And the tangent is always perpendicular to the normal. So a is a sort of a gratuitous function that we really don't need. It just comes in. So this scalar equation is, although it is two equations, a is arbitrary. So take a equal to 0. So that's our parameterization, a equal to 0. So now, here is a problem again. This is a domain d of t. There is a family gamma of t, the boundary values. We have to choose such a family of curves, x of t lambda, y of t lambda. Then solve this equation for u It's an equation in a square or in a rectangular domain where the Laplacian is 1 here and 0 elsewhere. Where there is a jump on the y derivative here, we solve it. Then we compute u sub x and u sub y. And then we get the derivative of the x dt dy dt. And then we integrate. After we get the x dt, we just integrate in t. We know the value initially. So we get from a family x of t lambda, y of t lambda, we get x tilde of t lambda, y tilde of t lambda. And we want to show that there is that this mapping has a fixed point. So it's a fixed point for not for a function or for a point in a Hilbert space or Banach space, or it's a fixed point for a family of curves. And this is what we in fact did. This is a joint paper with Velasquez. It appeared in the archive. I can give you a copy if you want. And we find that for some small time interval, there is in fact a solution, a unique solution. So there is a black spot here. There is a boundary, say. So here I'm writing it as y as a function of x and t. This function is a smooth function. And something very surprising happened. That when we try to see what is the shape of the boundary, this is what we got. So if you have a black spot on a document and you make a Xerox copy, you supposedly will find that the thickness of the toner tells you how dark it is. It's darker at the edge than in the middle. When I told it to a friend of mine in Kodak, he said, well, just comes to show you that the model is wrong. But when I talked to someone in Xerox, he said, oh yeah, we know that. It's called the edge effect. The edge picks up more color. So this is the edge effect. And it's most pronounced at the beginning. Now, here is an experiment you can conduct. You take the Xerox machine and put a page in, Xerox it, and put another one. Do it as fast as you can to get very close to the initial time. Don't let it stay there too long. And after a while, you'll find that it's not, it seems to deteriorate. The same page, just make it many times. And you'll find that you are, in fact, in the middle, it's lighter than in the boundary. Now, as I said, if you can get something like that, that will be perfect. But we never get it, and therefore, in fact, there is a theorem, you cannot get it. So the Xerox machine is not perfect. Someone can write probably a paper saying the Xerox machine is not perfect. Can never be perfect. And that's a theorem that says that you cannot have a boundary like this, and that follows from properties of analytic continuation of harmonic functions. It's so this is for small time. This is what happens. What happens when the time gets larger? Well, for larger times, in fact, I first looked with Bei-Hu on the case of the stationary problem, and t is infinity. So that means that on the boundary, the velocity became 0. So the normal derivative of u is 0. So you want to solve the problem with find a harmonic function in a square, not quite harmonic, but here Laplacian is 1, such that along this there is a jump in the y derivative, and the boundary on this boundary the normal derivative is equal to 0. Can you find a function which is a harmonic outside, inside the Laplacian u is 1, a little thing here, the normal derivative has a jump, and on this boundary the normal derivative of u is 0. The answer is, and so that this boundary will be straight line, will be sort of this shape that I wrote before. And the answer, you cannot. In fact, to try to solve this problem for general line here, this is an open problem. We don't know if there is a solution. So if I ask you, is there a solution to this problem where this is a straight line, this is an interval here, and I don't know if there is a solution, except in two special cases. One case that are not interesting from the point of view of industry. One is that the black spot is very, very small, and the second one, the black spot is very, very large. It's almost the whole interval. Usually cases are not extreme, so that they are in between. So neither case is really interesting, but except for mathematics, the mathematics of it. So if this interval is very, very small, there are infinite number of solutions. So that's quite amazing, which, what does it mean for the actual problem? So there are infinite number of solutions, and there are two components that are disconnected. And more recently, Bei-Hu and Li Wang proved that there is at least one component that is connected. At least one, there may be more. If this interval, the black spot is very, very small. On the other hand, if it is very, very large, then there is a unique solution. And as I drew here, and this is going from boundary here to boundary here. It's everything that you would like it to have, it has. It is monotone, and it's analytic, and all that stuff. But of course, rarely you get to Xerox something which is almost, to begin with, almost completely black. So that's, again, not particularly interesting. So we actually originally worked on this problem, and after we got frustrated, we couldn't really get, and the guy said, I'm going to change the problem. I'm really interested what happens in a very short time, because our machines are going to be faster and faster and faster. And it's the first time that someone changed the problem on us and made it easier. Not easier, but different. The time dependent became interesting. And that's what we did later on here. So there are other ways to model the Xerox machine. This is a continuous approach. You can also model it as particles, separate particles. And so the particles are running there, and you can use collision, and you can also use it without collision. There are different ways of doing it. I think at Xerox, I have seen a big effort in building up computational facilities for particles rather than continuous model. But you deal with particles, you cannot take more than maybe 100 particles. On the other hand, the number of toner particles is in the millions. So which model is more correct, who knows? Okay, I know I did not exceed my time, so are there any questions?
Questions?
Yes.
Recently, I wrote something on a sheet of colored paper, like maybe orange paper, and copied it. And if I remember right, of course, the whole copy was dark. What I had written was dark, but there was some relief around where I had written. It was, you could, even though the whole copy was dark, you could still read what was written because it was white right around where I had written. Can you think of any reason why that should be?
No, if you do colored copying, then there is another ingredient. So what happens is...
This wasn't a color copy.
Oh.
I just didn't use white paper.
Oh, you use a different...
The paper was like orange or something.
Yes.
And so that, the copies don't come out well.
Uh-huh.
When you put dark paper in. And it seemed like although the whole copy was dark, you could still read what was written because there was some relief right around what was written.
Yeah.
Does that?
I don't know, but well, the companies don't want you to use colored pages. In fact, they don't want to use any page except the paper that they manufacture. You know, the photocopying machine companies make money on two things. They don't make money on the machine, for sure. They sell it to you at loss. They make money on the paper, and they make money on the toner.
Okay, I won't do it anymore.
By the way, if you know, when you start the machine in the morning, you have to wait a few minutes. The reason you have to wait is the reason you have to wait is guess which stage you have to wait for. Something is not ready yet. It says not ready. What? I'm sorry? The fuse, exactly. It's this that is not ready. It takes time to heat. It's not the corona charge. This is instant. And everything here is fine. It's just the fuser. That's what it takes, the time that it takes. Now, if you have a colored copy, then you have toners of different colors. And then this has to go around with toners, one circle, comes back and get another layer, and then another layer. And then you get seated there, several layers of toners, different colors. And they start to mix together a little bit. They form like, almost like a composite material. I'm going to talk about composite material in half an hour. But and the question is, how do they squeeze each other, and how to create, you know, how the color should be as close to the original as possible. There are big issues.
Other questions? Okay, well, we will have the final lecture in about 30 minutes. We'll start right at 3 o'clock.
Suppose you take two kinds of material, two kinds of electric material, one material with conductivity K1 and the second one with conductivity K2. And you put one piece next to another, say in a periodic order. So you have K1, K2, K1, K2, K1 in some fixed interval. Okay, so if U is electric potential of this material, it's what? A, the derivative of U, or K gradient U, then you take the gradient or the derivative of this in one dimension equal to F. This is second order ordinary differential equation in one dimension in some interval between x0 and x1, and K epsilon, it keeps flipping from K1 to K2, K1 to K2 in a periodic way. So let's write it, and we are asking what happens when this material, it gets to be, this interval gets to be smaller and smaller and smaller. Suppose that we are making such a composite material with 100 million pieces, or let's say with micron size of K1, micron size of K2. So it'll be impossible to start to computing in each interval separately. You want to take the whole thing together and in some average sense see to what happens to the electric potential. So what is the limiting of the solution, limit of the solution u sub epsilon when epsilon goes to 0? So a good guess might be that you look at this function k sub epsilon, which is a periodic function of period epsilon. So a of y is one periodic, and you can write it as a of x over epsilon to make the period of size epsilon. And a will take the value plus 1 minus k1 or k2 in each period. Okay, so it's periodic. It has one value and then another value. Higher value, lower value, higher value, lower value. So in each period it will have two values, the higher and the lower. And you ask, so you look at this function, a, which is fast oscillating, a of x over epsilon. You average the a, so this is the average of a. And then the limiting u should satisfy that if you take the average of a, the average of this conductivity, you take the u prime, and take the derivative of all this should be equal to f. That seems natural. But that's also the wrong answer. So if you want to solve the limiting problem here, where k epsilon keep flipping, taking the average of k epsilon is the wrong answer. The correct answer is this. You take the average of 1 over a, you get a number, and then you take 1 over this average, and u prime and all this prime. This is the correct answer. So things are not what they seem. If you try to take this, this material and combine the with different conductivities, the limiting one, the effective conductivity is not the average. It's rather 1 over the average. In a sense, you can think of it as the difference between electric current, electric network, which is in parallel or in sequence. In parallel, the resistance, one of the reciprocals, as well as the resistance, is the sum of the reciprocals of the various resistances. And 1 over k is a resistance. So this is an example, simplest example of homogenization that tells you there is a formula there, but it's not the obvious one. And this can be generalized not only to one ordinary differential equation, but to partial differential equations, to systems of equations, and so on. There is a whole theory on homogenizations in hundreds of papers. Okay, now I'll give you a different example, since I'm interested in problems that, number one, come from industry, and number two, they are not in the standard theory. So here is something that came to us from Ford Motor Company. You know that there are various pushers for the development of science. One of them is government regulations. So the government would like that by a certain year, the average car that Ford Motor Company produces, or GM produces, or other companies, will make 30 miles per gallon. And they have to do it, or else they are going to have to pay penalties, heavy penalties. So they begin to think, how can we do that? What do we have to do to get higher mileage? And one possibility is to make materials lighter. Of course, you can drop the bumper, but then you break another government regulation. It says that you have to protect the driver with the bumper, that collision with 5 miles an hour will not damage the car. And by the way, this regulation has been dropped down. No one talks about it, but it's dropped because it's just impossible to make plastic bumpers. You need plastic bumpers basically in order to reduce the weight of the car, but you cannot. But they don't tolerate 5 miles an hour, a little less. So this is out of the out of the window, but it's not talked about much. Okay, so you like to reduce weights, and they make composite materials, like the one I described before. For instance, exchange rods that are used in automobiles used to be made of steel. Now they make them of aluminum, much lighter. But aluminum is breakable, is very brittle. So they reinforce it with carbon particles. So they process a material which is aluminum with carbon. It's a composite. And to this composite, you can apply homogenization. So these are examples where new mathematics is coming out of new models because of government regulations. Now, another area where you can reduce the weight is the gas tank in your car. It used to be made of metals. It's still made of metals in most cars. But Ford Motor Company is beginning to make fuel tank, gas tanks that are made of plastic. Okay, but plastic, you know, you can penetrate. Fuel can get out of plastic. If you have fuel here, it can get out. And there is a government regulation that says that when the car is in a resting position, is parked in your garage overnight, it's not allowed for it to leak more than a certain milligrams of fuel per 12 hours. There is some norms. There are all kinds of regulations. Therefore, a plastic tank is not very good because fuel does permeate through it. A larger proportion is allowed. So what they do, they take fluorine and they coat the inner part by a process which is called blow molding, sort of like that inside, because with a stronger power and hotter stuff. And they fill all the interior with this material, and now it reduces the permeation. But it doesn't do a perfect job. There are little holes everywhere. There's also a big hole where they do the molding, the blow molding. So the question that people asked one of the modelers in Ford was, what is the effect of all these holes? There are lots of them. What's the effect of them? Do they really interfere much with the permeation? So that was the question. So if we denote the density of the fuel in the tank inside by Q0, and that's more or less a constant, and this is the air. This is the air. This is the fuel. And in this little layer, which is maybe 1 millimeter, or maybe 2 millimeters, this is where we are going to study the problem, because that's where the fuel is leaking. It's leaking from density Q0 to density 0 in the air. Once they come to the air, it dissipates, and so it disappears, and density is 0. So Q0 is the density of the fuel in the tank, and C is in this thin layer, and I am now going to draw a picture that will show it more clearly. So, but I'll call Q0 minus C, I'll call it U. So we are interested in this region here, in this shell-like region. And there are holes here, see? And also parts that don't have holes, of course.